let's see here. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to just guide our steps today. Help us to understand more about curves and how to understand them with calculus and algebra and such. In your name I pray, Lord Jesus. Amen. So this is a silly family of examples we're looking at, and admittedly this is jumping ahead a bit. Like here I'm using, this is a polar, family of polar curves for different choices of A. We'll come back to this. I just was putting it up for kicks. But I wanted to play around with Desmos just for a second here. So let's go to a new one. Here's another silly one I have. Check this out. So, I mean, if you have enough time and really feel like it, you can make whatever you want with, parametrized curves. And what I'm doing here is I'm animating. Well, let's not explain this. It's not important. But what's that?
How many functions does that take?
At least 4. Let's see here. Come on, I want a new one. Let me get to a new one. Stupid thing.
Hey, what's monster?
Yeah. It's not that exciting, actually. Come on. Oh, there we go. There we go. So let's just try something simple. I mean, I'll start out real simple. X squared plus y squared equal to 1. We know what that is. That's a circle, right? One of the neat things about Desmos, you guys may not know this already, is you can add a slider, right? So then we can look at circles. We can adjust the radius, make it bigger, make it smaller. What happens when it's negative? There's no solution, right? So there's that. But of course you can do other more exciting things like, I don't know, multiply this by x cubed, see what happens. All right, now we're looking at, x squared plus y squared x cubed equals to a. And you can see what happens when you choose different values of a. I mean, you get really different looking curves here, right? So this, you got like two different branches, right? Like that. Let's see here. What else can we do? What if I was to put a, I don't know. What happens if I put a y cubed over here? What does that do? That's interesting. So, whoa, look at that. All of a sudden. So, yeah, let's think about this for a second here. So, let me choose a specific value rather than the slider. Let's suppose we put 1 there. There we go. All right. So let's talk about this curve. I mean, this is a curve, right? There are apparently 1, 2, 3 different branches of this curve, right? So is this a function? I mean, is this the graph of a single function? The answer is obviously no, right? This fails the vertical line test, like, badly, right? Like, if you put a vertical line right here, how many? You got 1, 2, 3 values, right? However, it does seem like if we're over here, if we have x less than 0, it looks like you've got the graph of a function, right? Now maybe if I zoom out, I'll find out there's other weird stuff outside our viewing scale, right? I don't know. I feel like no, but, on the other hand, you could have stuff like this, right?
Oh, good lord.
So, what can we make of this?
A rug.
A rug? A rug is a good answer. I think we can reasonably realize that, well, this equation contains fine detail that has not been fully resolved. You don't say. We're definitely past the numerical limit of Desmos at this scale, right? So, I mean, you have two options. Either, is it get better if we zoom in? Maybe. Kind of, sort of. Yeah. And it starts to make sense if you think about it. Sine of x squared plus y squared equals to 0.5. what do you need? You need inputs to sine to be what? Either, how do you get a half from sine? You need, what, 30 degrees, right? Or pi over 6, or plus 2 pi multiples of that, right? But there's also another solution, if you remember. So if you just think about sine, right? There's two solutions. There's one here, and there's one here, right? Pi over 6. And over here you got your 5 pi over 6. So that is what we need for x squared plus y squared to be equal to, right? So the first circle should be at radius square root of pi over 6. That's this one. This one's the square root of 5 pi over 6. Next, you've got pi over 6 plus 2 pi square root. That's that radius. And then, you know, 5 pi over 6 plus 2 pi square root, that radius, and so forth and so on. That's why you've got this sort of banding. So sometimes you can understand where the curves are coming from with some kind of principle like that. But if we go back to something like I had before, well, that one's not too exciting. I want more interesting than that. Let's put a x over here. There we go. All right, so I guess my question would, so this is harder than anything in your homework, but I just want to ask a question. Suppose you wanted to parametrize this curve. How would you do it? I mean, this might be too hard. Yep.
You can set x equal to r cosine theta and y equal to r sine theta. Substitute those in.
Oh. Whoa, that's hardcore. I don't know. But if I say x is equal to cosine theta, y is equal to sine theta, then I'm up against sine cubed theta plus, no, cosine cubed theta plus sine to the 4th theta plus sine squared times, no, cosine squared times sine cubed, all of that equal to cosine theta. That's bad. Listen, here's what we could do. So let me just walk through how I'd attack this problem, all right? So I start out with what I'm up against. X cubed, y to the 4th, plus x squared, y cubed, equal to x, right? And I need to have a more precise goal in mind. So let's suppose I'm trying to parameterize it up here. Let's choose the nice case, x and y both positive, all right? Let's assume we're looking for that branch. Goal, parameterize x and y both positive, right? With that assumption, I can simplify this equation. What can I do? I can divide by x, because x is non-zero. So I don't change the solution set in that regard. That gives me x squared, y to the 4th, plus x, y cubed, equal to 1. But y is non-zero, right? So I can divide by what? Well, I can divide by y cubed. I mean, why not, right? Oh, that's not as helpful as I'd hoped. See, but the trouble is this stupid 1 is still over here. Ah! See? Man. Rats. I thought I had something there for a second, but I realized if I divide by y cubed, what does it give me? X squared y plus x equals to 1 over. So it's like, you ever have one of those snakes with like the cloth thing with the beans inside of it, and you try to squeeze the beans to one side, and then you squeeze them to the other, but there's always beans in there. Like you can't ever. It's like. Nice. Wow, that was good. See, that's before, mostly before I was born. So that's especially biting. Like, nice, very nice. Let's see here. Sasser, you should learn from him. Okay, let's see. So, I would love to solve for y, but it seems like I can't quite do it, right? All right, so Man, any ideas? So what I'm looking for here, what I want in order to parameterize this is x is equal to some function of time, right? Y is equal to some other function of time, such that it solves this equation, or solves this equation, or solves that equation. And by golly, I don't know. I mean, I'm kind of at a loss here how to solve this one. So I will admit, I don't know how to parameterize this. All right? There are people who make their careers in mathematics finding a parameterization of something that hasn't been parameterized before. It's a creative process. Like, it doesn't have to be something you can do. Now, that said, there are tons of examples we can parameterize, right? So, I mean, I'm sorry, that's a little bit unsettling. Oh, well, we couldn't parameterize it, right? At least I don't see how to do it right off. I have a hard time giving up on things. Is it related to arc length? Yeah, well, I mean, see, perhaps I could find the arc length, but no, see, this is the trouble. To find the arc length, I need the parameterization. I have two formulas for arc length, the calculation of arc length. The one is for a parameterization of the curve. The other is for a graph. All right. But anyway. So, sorry to leave this kind of as an open question, but, you know, open question. Can you find these, right? I can't at the moment, so I'll have to try again, you know. Let's see here. Now, if I change this ever so slightly, right? If I do, say, x cubed y to the fourth plus x squared y cubed equal to 0, well, then I can parameterize it. See, because if I'm in this region where x and y is greater than 0, I can just divide this by what? I can divide by x. Let's see here. We'll factor out. What do we can factor out? We can factor out what? X squared, y cubed. What are we left with? Y plus what? 1? I think there's, oh, x, there's an xy. Yeah, thank you. I was like, that seems too easy. Right? So in this regard, if I'm in this context, if I'm where xy is greater than 0, how I can do what? I can say, I just need xy plus 1 equal to 0, right? So parametric equations for this, easy enough to find, right? In fact, I can solve for y, right? Y is equal to minus 1 over x. Yeah, if you want to write, you can write parametrically. We could say x equals to t, y equals to minus 1 over t. There you go. These are parametric equations for my slightly modified problem. See how it works out different if I put a 0 there? Well, it's not so exciting, is it? See? Oh! Oof. Oof. There's just one problem. There's just one problem. We've gone looking for something that doesn't exist. See, because this curve, it's not up in quadrant 1, is it? So the algebra is misleading, right? Because is it possible? Let's see here. Let's see, what's the issue? Well, the issue is that x and y are not both. If I do this, I can't have. I mean, let me just get to the point here. And this is my bad. Xy equals to minus 1, right? Can you achieve this in quadrant 1? You cannot, right? Right. So exactly. So what have we found here inadvertently? Quadrant 2 and quadrant. So in quadrant 2 or 3, right? As you can see, right? Y equals minus x. Is this one or that one? Oh, 2 and 4. Sorry, I can't count. Right? What's the other thing that's going on here? What's this here? Yeah, y equals 0, right? So if you look at this, right? If you put y equals to 0, does it solve that equation? It sure does. So the x-axis is a solution. And is Desmos infallible?
Yes.
It is not. Because it is missing a very obvious solution, namely this one. Right? Can x be 0 and solve this equation? It can. That's also a solution, right? Do you agree? I hope you agree. So how do we parameterize an equation? The answer is, it's complicated in general. You have to think through cases, all right? I wanted to try something off the grid, so to speak, with you guys, just to explore a little bit. We don't usually do this too much in here, because usually I have, you know, a plan, someplace to get to, stuff like that. So let me get back into the pre-planned programming in here. Let me get rid of this. Come on, go, shoot out.
So if you parameterize y, x, whereas your parameterization is just x equals t.
If I parameterize, if I what?
You have the equation, you've parameterized y.
Yeah.
Y equals negative 1 over t. Do you need
No. I have parameterized the curve.
the curve in terms of y?
And I parameterized the curve in terms of t. You could, I think you could
You need to have another parameterization for in terms of t and x.
Do I need to have another parameterization in terms of t and x? No, I don't think so. I mean, this is a parameterization of the curve we were looking at in quadrants 2 or 4. Now, you can talk about other parameterizations for other parts, right? There's 2 other ones that I can think of that we were just talking about. The other one would be x equals to 0, y equals to t. The other one would be x equals to t, y equals to 0. So these are the parametric equations for the what? X equals to 0, y is varying. We're talking about the y-axis, right? So this is a parameterization of the y-axis. This guy down here, this is a parameterization of the x-axis. So these, and again, you know, we could talk about those in terms of like R1 of t equal to, no, oh, wait a minute. Well, it's fine. It's just weird. Well, let me just say a little bit more. So this t, I mean, I would be inclined to do more of this, all right? Golly. Well, fine. So this would be for t an element of, let's say, 0 to infinity. This would be for t an element of minus infinity. So this is weird. I don't usually do this, right? Just it here. This is just for t in the reals. This is also for t in the reals, all right? Some people would insist that the parameterization be done with what's called a connected domain, all right? So to be fussy, over here, this parameterization, it doesn't make sense for t equals to 0, right? So you could say, well, you're really doing these equations for all t. It's just that, you know, you have minus infinity to 0, not included in 0 to infinity, right? But a lot of the ways we think about parameterized curves, we like to have the domain connected. So it would be more reasonable to give 2 parameterizations, one for like the left and one for the right piece of that, the hyperbola. And then, you know, this is the x-axis, this is the, wait a minute, no, other way around. This is the y-axis, this is the x-axis, parametrized. All right, enough about that. So just, let me just take a step back here. The basic idea is a parametrized curve is an assignment of t mapping to r of t. So this r of t is really a pair of things, all right? X of t and y of t. So you need to give two functions of the parameter, right? And it's not just that. Like, it's not enough just to give the equation. The parametric equations are not enough, all right? What I've written here is really not enough. This is an insufficient description. Why? Because part of saying what a parametrized curve is declaring the domain of the parameter. Like, you have to do that, otherwise it's not really clear. So this is for t in, you know, some interval I. So that sometimes can be the whole real line, sometimes it's a closed interval. Most of the time it's a closed interval for us, all right? But a parametrized curve is an assignment of t to a pair of functions of t over some range of values of t. The way to think about this is it's like you're taking the real, you know, taking some subset of the real numbers. Let's picture it for a second here as I, all right? And what the mapping R does, all right? What this mapping R does is it takes it and it puts it in the plane, all right? It puts it in the plane and it makes it into whatever kind of curve you're looking for, all right? It takes this little, you know, interval of real numbers and it bends it around or whatever and makes it this curve, all right? So over here you're looking at R of I, which is a subset of the plane, all right? This is the idea. So t is not something based on the plane. T is something based on the curve we're considering. And more than that, for a given curve, there's tons of different parameterizations. Like, let's look at a specific example of what I'm talking about. So let's see here. How about this? Well, I guess that was example one. Here's a more reasonable example one. We could have something like, you know, x squared. Let's see here. X squared plus 3y squared equals to 1. All right? Suppose you want to find a parameterization of this curve. How do you do it? Well, what I do with something like this is I go, well, I'm thinking cosine squared t plus sine squared t is equal to 1. So it's kind of like that, right? But it's not quite that right pattern, right? So maybe I can put x equals to cosine t. That should work, right? And what should I do to sine? I mean, y. Because I want 3y squared to be sine squared, right? So what should I make y equal to make that 3 go away? What's that? Yeah, 1 over the square root of 3 times sine t, right? If I do this, then when I look at the square root of 3 times y and I square it, that's 3y squared and that's sine squared, right? What am I saying? I'm saying if you take these, right? If you take these equations, right, and you plug them back in here, right, it's true. That's what's required for that to be a parameterization of the curve. Now, what curve are we talking about here? Do you guys know what this is? Exactly. This is an ellipse, right? So you may or may not have seen that. We will take some more time in class to talk more systematically about hyperbolas and ellipses and things. I have a day devoted for conic sections, but I don't want to do that right now. I want to talk about the calculus of curves before we talk about the algebra of conic sections, okay? But that is an ellipse, that's true, and there's the parameterization of the ellipse. Is that the only one? What's this parameterization look like? How's it work? Let's think about it. It's kind of easy to think about. Maybe that's why. This is x, right? So think about it. What does x range over? Plus to minus 1, right? So the furthest x goes out is 1 and minus 1. How about y? y is ranging between 1 over root 3 to minus 1 over root 3, right? Whatever that is. It's less than 1 though, right? So like that. And where's t equal to 0? Well, this is t equals to 0. This up here is t equals to pi over 2. Over here you got t equals to pi. Down here you got t equals to 3 pi over 2. So apparently the parameterization is doing what? It's going from here to there, to over to here, like that, right? And so you notice something about the parameterization. It has a direction, right? It's going this way. This is called what? This is called counterclockwise, right? It has a counterclockwise orientation. Oh, I mean the vector symbol? Yeah, fair enough. But we draw these little arrows to indicate the direction. So, question. This up here, is that oriented? Like the ellipse, is it counterclockwise or clockwise oriented? The answer is it's neither, right? It's an equation. It doesn't have an orientation unless you give it one, right? So one of the things that's immediately obvious is you could take these same equations, right? And if you switch, and so what's my, I guess I got done berating not giving the domain. So here I mean 0 less than or equal to t less than or equal to 2 pi, right? So my I for this one would be 0 to 2 pi. All right. If you wanted to find another parameterization of this ellipse, you have many choices, right? One thing you could do, which would be kind of silly, is you could just put a square here. It still solves the equation. What's the difference? Let me write that as a separate example. So if we had x equals to cosine of t squared, y equals to 1 over root 3 sine of t squared, right? And to be fair, 0 less than or equal to t less than or equal to this time square root of 2 pi, right? That would be a different parameterization of the same curve. It would start at the same point, though. It would still start at, 1, 0. It would go around the loop. But what would be the difference? What's the difference if I start, what's the difference between this parameterization and that one? It speeds up, right? All right. So we should, I think I've talked enough about how to parameterize a curve and how to check a parameterization. You have some homework which will hopefully make this sink in more. All right. But well, we'll do more examples. I think I should move on to the calculus for the moment, though. All right, so, and by the way, I could just as well put a cube or a 4th power, right? I could take the original t and just multiply by 3 and do 2 pi over 3. The choices are endless. There are infinitely many parameterizations for a given curve. So as an instructor, it's a very dangerous thing to give you guys an equation and say, find a parameterization. Because I have to be ready for infinitely many correct answers. And finitely many wrong ones. Right? Because there's only like 30 of you, right? So, and none of you are going to create infinitely many wrong answers. It's just not like, no one's going to spend the time, right? Just to make me a liar? No? Okay. maybe Sasser, I don't know, but let's see here. Where am I? Oh yes, so calculus. So, given, let's say t maps to a vector of t. So here we've got like a1 as a function of time, a2 as a function of time, all right? So this is what is this? This is a vector valued function of time. We can define derivative, we can define integral, but let me just stick to the derivative here. dA dt is equal to dA1 dt, comma dA2 dt. You're like, this is wrong. If you're making a definition of the derivative, you should be doing it from a limiting process. You're right, you caught me. I'm shortcutting the limiting definition as to not build more ill will into the calculus 2 population at this point, right? So you prefer this definition. But yeah, okay, fine. You could take the limiting, like the limit is, you know, t plus h minus a of t, divide by h. Take the limit as t goes to 0, h goes to 0, and then you get this. All right? But this is the definition. All right? And what would the integral be? What would we mean by this? Well, we would just mean integrate a1 of t dt, integrate a2 of t dt. All right? So if you take the integral of a vector valued function, you integrate component-wise. And we could do this in the definite sense or the indefinite sense, right? You could add bounds if you want. So let's see here, theorem. If you've got the derivative with respect to time, all right, of a function of t times this vector valued function of t, how's that work? Let's work it out. So how do you multiply a vector times a function? How's that work? You have f times a1, f times a2, right? Remember how we defined scalar multiplication last time? It's still true when we look at functions of time times vector valued functions of time. Same definition. And then we do what? We differentiate with respect to time fa1, differentiate with respect to time fa2. All right? Now what are we up against? Those are products, right? What do we have to do? The product rule, right? So this gives me df dt times a1 plus f times da1 dt. Likewise over here, df dt a2 plus f da2 dt. All right, now we need to group some things, right? We can factor out the df dt times a1, a2, and we can factor out the f, and we've got da1 dt, da2 dt. And what is that? The answer here should be very unsurprising, actually. So we've got df dt times a vector plus f times dA vector dt. Which is an extension of the product rule that you already know, but now for a function times a vector of functions. A simple application of this, what would happen if f is a constant? Corollary. What if I have ddt of like a constant times the vector? What's that going to be equal to? The derivative of the constant, right? Times a plus the constant times dA dt. But what's the derivative of a constant? 0, right? So we just get the constant times dA dt. Sadly, I do not have my shirt or the juice. So with the humidity today, that's going to happen. All right, so another example. What if you have, well, I needed to make some more definitions here. So let's say R as a function of t is position. V as a function of t is equal to dr dt. This is velocity. The acceleration at time t is equal to dv dt, right? Which is equal to d squared r dt squared. This is acceleration, right? So in 2 dimensions, properly speaking, the position, the velocity, and the acceleration, these are all vectors, all right? So a fun 2-dimensional example to talk to you guys about is just this one. If we have the acceleration is constant, right? And the acceleration is equal to, let's say, 0 minus g. What happens if you integrate this? Actually, let me turn the tables here. Let me just pull something from the thin blue sky. Let me turn the tables, make it easier for us to understand. So let's suppose that r of t is equal to, let's say, r naught, which is a constant, plus t times v naught, which is a constant, minus, well, rather plus, fine, 0, minus 1/2 gt squared. So again, constant vector, like this. What happens when we differentiate this? How's dr dt look like? So the velocity dr dt. So if this is a constant vector, what's its derivative? 0, right? What happens when we differentiate t times v naught? How's that work? So this is the flip side of my previous example, right? What if the vector is a constant and the function's not? So t is playing the role of f of t in that example on the far board. So in this case, basically, the v naught just pulls out, and this differentiates to v naught, right? So let me just, this differentiates to v naught. How about this? What happens? You differentiate this, you get what? What's the derivative of this? With respect to t, it's what? Minus, so we get minus gt, right? Differentiate again, what do we get? dv dt. So this is 0 when it differentiates to 0, and this differentiates to what? 0 minus g, right? So what you're looking at here, what I wrote for you, the top equation is the equations of motion for constant gravitational acceleration downward of minus g. Here's the velocity as a function of time. The x velocity doesn't change because this is just constant, right? And down here, we have the constant acceleration downward of minus g. All right. So not really my main goal in here, but I want to show you that you can think about physics in terms of a vector notation, and it brings things together. The x and the y are put together in one unified story, right? All right, so, but we need to come back to the world of parametric equations. So let's drag me back to the world of parametric equations, kicking and screaming, but I'll come back. So before I do that, though, let me make a definition for you. So given, you know, R from I to R2 parametrizes C, and T naught is an element of I, such that R prime of T naught exists, then let's say I need something else. I'll use L. L of T equals to R of T naught plus R prime of t naught times t minus t naught defines the colliding tangent line. Colliding tangent line to C at the point we're talking about, R of t naught. So I think I've given you some homework problems where I ask you to find the parametrization of the colliding tangent line. This is it, all right? Let me show you an example of this, yeah? So example 4. So we could have something like, suppose you have parametrization R of t equal to, oh, I don't know, t squared cosine of t there. All right. And let's examine t naught equals to 1. Let's find the colliding tangent line there. All right. So see, this purple marker is no longer with us. I think the rest of the lecture is going to be monochromatic. Oh well. So what is the velocity here? We do dr dt, right? What do we get? We get 2t minus sine t. So then what is r prime of 1? Do you remember in Calculus 1 you were asked to find the equation of the tangent line? You differentiated it. And then many of you, about half of you, lost points because you wrote the equation of the tangent line without plugging in the point. Right? You had a tangent line equation where you had like a cube in your formula. No, maybe you guys did not make this mistake, but every Calculus 1 I've ever taught, like students do not actually plug the point in, but this is important. We have to plug the number in to get the tangent, to get the velocity vector at that time, right? The function of time, plug in t equal to 1, we get 2 minus sine of 1. So it's important. This vector right here is a constant vector, all right? Just like this. And so then the parametrization, L of t equal to, what is it? R of t. What is R of t naught here? What's R of 1? We get what? 1 cosine of 1, right? And so what I have is I've got 1 comma cosine of 1 plus what? 2 minus sine of 1 times what? Times t minus 1. Now I can clean this up a bit. We have 3, well, excuse me, I have 1 plus twice t minus 1, comma, cosine of 1 minus 2 times the sine of 1 times t minus 1. So, well, listen, I'll put vectors here. Like I said, it's kind of a matter of emphasis. So, sorry if I have put the wrong emphasis on the incorrect syllable. But there you go. So there you go. That's the colliding tangent line. The reason it's called the colliding tangent line, right, is if we were to draw both of these, and I'm afraid to do that, but I don't know what this thing looks like, right? I'd have to get the computer back out to do that. But the point, yep.
Did you need to put angle brackets around the word cosine 1?
Yeah. Like I said, I mean, you could put them both places if you want. They're equal. It's a matter of emphasis. So, if we plug in time 1, right? Notice that L of 1 is equal to R of 1. So at that time, both of these parametrized curves meet. All right? So like whatever this thing looks like, I don't know what it looks like. Maybe it looks like this, right? Here's maybe a picture of r of t. Here's r of 1. Let's call that point P, since I'm tired of writing the other thing. That's the point P, right? The tangent line, well, it's a tangent line. It has the meaning of tangent line that you know, right? So like that. That point right there is also L of 1, right? And I don't know, just as a heuristic picture, but if the curve is going this way, then the tangent line is also going that way, right? And the direction of the tangent line is the velocity vector, this r prime of t naught. So what do I mean by colliding versus intersecting? I mean, there's something we also need to talk a little bit about here. It's hard for me to come up with examples that don't waste an inordinate amount of our time on this, because it's kind of a complicated thing to work out for a specific example. It's a pretty easy thing to understand, right? Unfortunately, I don't have enough colors and markers to do this at the moment, but so colliding versus intersecting, let's talk about that. So let's suppose we have R1 of t is, I don't know, let's make it pretty simple. Cosine t, sine t. That's a pretty simple one, right? R2 of t, let's say is, I don't know, 0.5 t. These two paths, this is a parameterization of two paths. Can you tell me geometrically what we're looking at? Now, to be clear, I should tell you 0 less than or equal to t less than or equal to 2 pi, and this one I'll let 0 less than or equal to t less than or equal to 1 for the sake of specificity. Can you plot these? Yes, sir.
It's a vertical line in a circle.
Vertical line in a circle. I almost agree with that. So, I mostly agree with that. You're right about the circle for sure, right? Here's I'm just setting the scale here, x and y axis, right? That R2, where does it go? It's a vertical line. I agree with you. Right here, right? How far does it go? To right here, right? So I would say you're mostly right. But to be clear, it's a vertical line segment, right? So a line goes on and on, right? So I'm not correcting you much. I think you have the right idea, Sam. These curves are definitely intersecting, right? By the way, these curves were also intersecting in my example 4. But are they colliding? What do we mean by colliding? So they intersect right here, right? How could you find out what time that happens at? For R2, what do you need? You need 0.5 squared, right? Plus t squared equals to what? 1, right? Because the equation of the circle is x squared plus y squared equals to 1. So it's that time for the purple line that you need to get to that point, right? Which is what? T is equal to the square root of whatever it is, 0.75, right? When you plug in that time into R1, are you at the same point? Like, what is R1 of, the square root of 0.75? What's that work out to? If it's the same point, I am the most unlucky person. I guess if it's the same point, I'll have to shave my head. Ooh, wait a minute. Well, that's not really much of a sacrifice, is it? Let's see here. Let's see here. Oh, do I want degrees? No, I do not want degrees. This is calculus. We are working in radians mode for cosine to square root 0.75. So I get 0.64. Whew, that was a relief. 0.65. 0.65, comma. .76. So as you can see, the key point is it's not equal to, 0.5, comma, the square root of 0.75. Right? Oh, wait a minute. No, it's not. For two vectors to be equal, they have to be equal. Both things have to match up, all right? So one matching up isn't enough, so I don't even have to worry about it. So here's a question. How do you decide whether two arbitrary paths have a point of... All right, so here's the difference. Just to, let me kind of lay down, just in case you ever come up against this problem in whatever context. Basically, it's just this. Intersection. If you're looking for points of intersection, you're trying to see, can you find a time such that R of t1 is equal to R of t2? Excuse me, R2 of t. So if you're looking for two paths, if they have a point of oh, my good grief. Sorry guys, S. You don't have to have the same parameter for both paths. A point of intersection could just be a place where the paths cross. They don't have to cross at the same time. If you like, you could put this be like T1, this be T2. But collision, that means that your two paths collide. In other words, they actually reach the same point at the same time. Right? And I admit, we are using the idea of the parameter being time. All right. Let me go on here. So something I should champion here is that our idea of tangent line just became much more general. See, because for a tangent line in calculus 1, for a curve, a graph, right, could you have a vertical line? You couldn't, right? But here, it's a simple matter. A vertical line is just one where the velocity vector points directly upward. That just means that r prime of t naught has the form 0 positive constant. That's a vector that points straight up, right? So there is no direction that is not permissible by this. This treats all directions on the same footing. So that's one of the beauties of the parametric viewpoint, is that there is no distinction really between x and y. All right? Nevertheless, calculus books like to ask certain questions that reduce to things we talked about already in calculus 1. All right? So like what's a common question for calculus 1? What's dy dx, right? That's the first thing. So let's talk about calculus 1 via parametrics. So in other words, given x is equal to, x of t, and y is equal to y of t, right? How to calculate like dy dx and d squared y, dx squared, things like this. Now, if you like, I could replace x of t with a different letter, and I could replace y of t with a different letter. I prefer not to do that because then you're like, well, what does this letter mean? And I think it's better to just write this x equals x of t, y equals y of t, even though the more purists in the mathematical community hate it. They hate it with a pure hatred. But engineers use this notation. We use a letter, we write it again with another letter to express that this we're thinking of as a function of time. And this we're thinking of as a function of time. So I don't think I do you any service by avoiding this notation, because this notation is used. So I'm going to use it. All right? Okay, so how do you calculate dy dx? It's very complicated, so pay close attention. It's like this. That's it. If you want me to derive it, I could, perhaps. So, you know, the tangent line, what was it? It's like it's like r of t naught plus what? R prime of t naught. And we could do times t, just to make things simple. Good grief, at t minus t naught, my bad. Fine, I'll stick with that. So this was the tangent line, right? And this right here, if we expand in detail, is what? It is dx dt at t naught, dy dt at t naught, right? So let me picture that. We're talking about the tangent line. Let me draw it as if it's going through this point here. Here's the point good grief. Fine, this point right here is my point of tangency. Let's say that's where r of t naught is. All right? This vector points like this, right? So what's going on? You're going this far over, dx dt of t naught. You're going this far up, dy dt of t naught. What is the slope of the tangent line? Dy dt divided by dx dt. This right here. So to be more pedantic, dy dx, you get buried in the indices here. Dy dx at x of t naught, comma y of t naught is equal to division dy dt of t naught dx dt of t naught. There you go. Now this formula is limited, right? This formula only makes sense for the curves that are parametrized in such a way what? In such a way that they, at least locally, resemble the graph of a function. So this formula will cease to make sense when you've got a vertical tangent, right? But the parametrized viewpoint still makes sense. It's just that this formula breaks down there, right? Because that's exactly where calculus 1 can't go. Vertical lines. Does this make sense? I mean, we can put it into practice. What's the slope of the tangent line here? What's dy dx at the point? What was the point? The point was 1 comma cosine 1. Yeah? What's the slope there? The ratio of the velocity vectors y and x components, namely minus sine of 1 and 2. So there you go. There's the slope of the tangent line right there. And you could also calculate it as a function of time, right? Do you see that? Like if I go back to example 5 over here, we can calculate dy dx at time t as equal to ddt of y, which was sine, let's say, over ddt of cosine, like that, and we get cosine t over minus sine t. So you could